So probably let me officially welcome you at this seminar of GOAT Research Group. And today's speaker will be Ágnes Cseh, who will be giving a talk about Pareto optimal coalitions of fixed size. So Ágnes, the stage is yours.
Thank you very much, Dushan, and thank you very much for the invitation. As I said, this is a work from last year, actually, but still quite current. This is a very cute topic, so this is why I chose this for this shorter talk. I will end with some open questions at the end, which are supposed to initiate collaborations between like Berlin and your group. Co-authors on this is Tamás Freiner and Petra Harjan, both of them are from the University of Technology, Budapest. I will talk about the setting first, and I will take it slow to define the exact setting. In general, we have n players who have to be partitioned into k rooms. Now, the rooms have no specific features. There are no nice rooms and ugly rooms. They only have a capacity, how many people they can accommodate, small or big rooms. And there are exactly as many beds in these, say, dormitory rooms as students, like n of them. And it matters for the students with whom they are placed together within a room. They don't care about the room qualities. As I said, they don't have too many qualities, but it does matter who their roommates are. So each player submits a preference list over the other players who will potentially become their roommates. I'll specify the exact type of preference list here a bit later. So our task as a mechanism designer's task is to partition these players into coalitions, into rooms, so that these fill all the rooms, and they also fulfill an additional optimality criterion based on the preferences we collected at the beginning. I'll specify this criterion a bit later. So for example, this is an instance, and this is the instance I will use to illustrate the notions later. We have the 9 players, 1 to 9 listed, and there are 3 rooms, with each with capacities 2, 3, and 4 respectively. Notice that these 3 add up to 9 exactly. So the number of beds equals the number of players. And the preferences lists are as follows. So the first player, who is here in the top left corner, his or her preference list is favorite roommate would be number 5, second favorite number 4, and she really does not like number 2. But everybody lists everybody else in this instance at the moment. So this is a sample instance. And our task is to group these 9 people into rooms of capacity 2, 3, and 4, so that they are happy, somehow happy. This is a very, very basic setting of basically coalition formation based on preferences. This is a feasible solution. So the blue room has capacity 2, the orange room has capacity 4, and the green room has capacity 3. Now, we want to make these people happy, and it's hard to define what happy is. There are several notions for happiness here. For example, if I ask how happy number 6 is, then the answer is, well, depends on how you define this, because number 6 is together with her first choice 7 in the orange room. So number 6 is super happy because her best girlfriend is there. But at the same time, if you go along the end of the list, then you see that number 6 is also put together with number 3, whom she hates most. So there are notions, different notions how to define what trade-off is good for the players. And we went for the classical settings, which we found in the literature, and we picked always 2 variants of the classical settings, and 2 variants in 4 categories. So these are the 4 points. The first point is exactly what I just talked about. How do you tell how happy a person is? So a player satisfaction can be very, very simply measured by taking the best or the worst player in the room. So if I have a choice between 2 rooms, then I measured the quality of these 2 rooms based on only the best player only the best roommate in this room, or in the other setting, only the worst roommate in this room for me. So these are options. The mechanism designer can later decide whether they want to go for the best or the worst roommate. There is no other option we offer in this work at the moment. Another option that the specific application could decide whether I require the completeness of the preferences. So in the previous example, everybody listed everybody else, but this is a sort of overdone requirement. If you have like very large dormitories, you can expect everybody to ask the other 100 students. So then you can go for incomplete lists if you like. It depends on the person who initiates this collaboration with the mechanism designer, whatever. However, if you assume that that this can be incomplete, then this means that edges that are not there also cannot be in the final solution, saying that if person A did not list a person B, then A cannot be put together with B. So usually applications work the way that they require everybody to list everybody else, but the list practically looks like you list your favorite 3 choices, and then you put everybody else in a single huge tie, so that everything is feasible in a sense. It's just you don't care who you get if you get somebody from the remaining 97 people there. Then the third property, which you can decide which side you flip it on, is that these lists are strictly or weakly ordered. You saw strictly ordered lists so far. Everybody in this full preference list was better than everybody else after this person on the list. But as I said previously, practically it's very often a weakly ordered list, exactly because people you don't know, you should not classify, right? So they are just in a big tie. And there is one very deciding factor, which will be important from the complexity point of view solely, and this is what the room capacity is. So our setting discusses 3 bedrooms and more than 3 bedrooms separately, because you guys know complexity well enough, so you will know that 3 is a magic number for complexity barrier. It is the same case here as well. Is it clear what these truths are? I can sort of flip on and off. I still haven't defined the optimality criterion. Yeah, anytime you have questions, do ask me.
So maybe let me ask, like, why is this, like, I am only with people on my preference list necessary, or?
This makes a huge difference in complexity. So it's not necessarily in the sense that we don't enforce, so our results are not valid only in the requirement, only in absence of in presence of the requirement that lists are complete. We also have results for incomplete lists, but the complexity changes radically, like really radically. That's the most important milestone for complexity.
Okay.
That's the only reason why I separate the 2 cases.
Okay, thank you.
More questions? Not now. Okay. So now finally, optimality criterion. What do we want to reach? How do we measure global happiness? I told you in the previous slides how we measure the happiness of a single person in one coalition versus in the other coalition, but how do we measure optimality for the entire instance? Where good old Pareto optimality. Nothing fancy. An assignment is Pareto optimal if there is no other assignment which makes nobody worse off, but at least one person better off. Pareto optimality is bad, so many people don't like to call it optimal because it's basically stable in a sense that you cannot convince everybody to change from here. But many assignments which do injustice to people are just Pareto optimal because they make one person happy and this person should just be made a bit worse off. And this is impossible in Pareto optimality, even though everybody else would profit from it. So it's a very strong assumption, and it's not the best optimality notion for applications, not for all of them, but it's one of the basic notions in correlations of their preferences. And then the very usual questions which any theoretical computer scientist would ask. What is the complexity of deciding whether a given assignment is Pareto optimal? So that's just a verification question. There's an existence question. What is the complexity of deciding whether there exists at all a Pareto optimal assignment? And then if so, then what is the complexity of finding this Pareto optimal assignment? Usual 3 questions for all TCS problems. So this is basically the map. I will go through each of the settings. If you see that this is 2 times 2 times 2 times 2, 16 settings. and to each setting 3 questions. So that's a lot, but I only have like 20-25 minutes, so I will go through them very quickly because you can bundle them and then they are dealt with together, which is good. There is literature on this, vast amount of literature on this. Most importantly, this is a sort of hedonic game. This is a very restricted sort of hedonic game because I tell you what sort of coalitions are allowed and I tell you how these coalitions are measured by the players. But a much more general study was done by Harris and co-authors, and they also cover some of the cases we cover, and so we just cite them here and there. Interestingly, I have not defined 2-person rooms because this has been done before, exactly in the same settings we have, and there's a polynomial algorithm for basically all cases to decide existence, and if a solution exists, then I also output it. And there are also variants which are related. Hedonic games and 2-person rooms were essentially the same questions in a slightly restricted or more general setting. 3-sided games, room-roommate games, and preferences depending on room size, the last 3 points, they are related in a sense that similar questions in a sort of different environment. So my favorite one is probably the room-roommate games. There they have 2-person rooms, and they have to assign 2 persons to each room. And the persons have preferences on the roommate and on the room as well. The rooms don't have preferences at all. So our setting is only different basically in the sense that we only have preferences on persons, but if you assume that the room is a person, then our setting is only different in some persons don't have preferences. So they are really very closely related literature pieces, but there was still a gap which we managed to fill. So first verification question, how do you decide whether a given assignment which is feasible is also Pareto optimal? And there, remember, 16 variants of this problem that we defined. These are the 16 variants, just for remembering them. But answer is very easy, everything is hard. We used 2 separate proofs because we couldn't cover all the 16 cases, but we could cover 8 and 8 cases. I don't like to show hardness proofs in talks because they usually are only interesting for people who are deep into this topic. But I like to say that these problems reduce from triangle packing, directed and undirected version, but the 2 proofs are different, which is nice, I think. It's a similar problem, but different proofs. Any question to this verification? Okay. So we are done with the first question. Second one is existence. What is the complexity of deciding whether there is at all a Pareto optimal assignment? If I'm given an assignment, I cannot decide in polytime whether it is Pareto optimal or not, but maybe there always exists one. So the answer is a bit more complicated to this than to the earlier question. This is the map of our results. So the question, is there a Pareto optimal assignment, becomes NP complete immediately if lists are incomplete. So this is sort of an answer for Andrea's question. If you assume that lists are incomplete, then you cannot really pack people into rooms so that it's feasible because triangle packing is hard. And you haven't really taken a look at the preferences at all. You just use the requirement that there's a partition problem. So you have to place everybody to some room. And already that makes it hard. So if you don't want to, if you are really owning a dormitory and if you want to make your life easier, you assume that everybody lists up everybody else. Otherwise you don't have a feasible solution. So we just go for it. We assume that everybody lists up everybody else in the instance. So we have complete list. Then there is always a Pareto optimal assignment. And the reason is only that, as usual for Pareto optimal assignments, there is a finite number of feasible solutions. We are in discrete setting. So it can't be the case that one assignment is better than the other one and there is better than the other one. So Pareto optimal cannot cycle in this sense because it has a very trivial potential function in it. So nobody gets worse off, at least one person gets better off. You cannot repeat this infinitely many times. So there must be somewhere a Pareto optimal solution, as always in discrete setting. So depending on the completeness of the preference list, either the problem is NP complete or there's always a solution. And this basically finishes the answer for the existence question. But here comes the third question. Okay, so I know there is always a Pareto optimal solution. Good, then let's find it once it exists all the time. So that's not that easy. And that's the second pink bubble here in the middle. How to find this guaranteedly existing Pareto optimal assignment, where you have to separate the cases based on whether the lists are strictly ordered or weakly ordered. If they are weakly ordered, there are ties on them. That's the most typical setting in applications, I assume. Then we separated best and the coalition evaluation based on the best or the worst roommate, and we provided two separate hardness proofs for this case. So if there are ties in the lists, then there is no polynomial time algorithm that could solve this. It's a bit weird because I didn't write NP complete there, because you always know there is a solution. But if you can output one, then at the same time, you can solve an NP complete problem. So it's a strange class of problems. It's not like there is a solution if and only if. You can output a solution if and only if, basically.
So is it like PPAD hard or?
No, we dug deep to classify what it is exactly. Okay. We dug so deep that I consulted 2 or 3 experts in complexity, like not like me, who just classifies problems in the CETL category, and they did not know whether there is a category for this. But they appear to be in abundance for Pareto optimality. It's not the only setting where they are there. So Harris and co-authors had the same sort of results for hedonic games. They didn't realize because they're not that much of complexity people. And I even asked Harris, and he was like, yeah, that's strange. That's a strange category. Nobody knows how it is called yet.
Okay, thanks.
Yeah. So the lower branch of this is hopeless. So let's go up. I have complete and strictly ordered list. Then, if the worst roommate matters, then I have a variant of serial dictatorship, which I will show you. If the best roommate matters, then depending on how large your rooms are, either you end up with a hard variant, or if all your rooms are of capacity 3, then you end up with serial dictatorship. So out of these 16 variants, you basically have 3 which are solvable. The upper one, this complete strict list, best roommate counts, and only 3-person rooms. And here there are 2 variants basically, because this serial dictatorship works for 3-person rooms and more person rooms as well. So what we did was basically drawing the entire complexity landscape of this setting. And everybody likes serial dictatorship, I think. So let's go through these three variants of serial dictatorship. And I would really be happy if you would guess these algorithms, because they're quite cute. I think they're easy to guess. So first variant, I will have 3 of these slides, 3 sets of these slides. And that's it basically. We have strict and complete lists. Only the best roommate matters. Everybody tries to minimize the rank of the best roommate in these preferences. And there are only 3-person rooms. So this was the case up here, the uppermost bubble. Our task is to come up with a variant of the serial dictatorship algorithm. You can do whatever you want. You design the algorithm, but it should be some serial dictatorship kind of algorithm. So the output is necessarily Pareto optimal. There should not be another assignment, which makes nobody worse off, but at least one person better off. So first task in this is to make number one, who is the dictator in the first round, choose her roommate, or do whatever she wants. She's a dictator. And her goal is to find the best roommate in her coalition. So what's her step?
It's like 5 and 4.
Okay, so Dushan's guess was to take 5 and 4 and then fix this as a room. Okay, and then number 2 will just take her favorite 2 and so on. Why is it wrong? Thank you. You are my educational example. What does 1 care about? Number 1.
Just about the best.
Yeah. So for 1, it doesn't matter whether she takes 5 and 4 or 5 and 2, or 5 and a dog. She doesn't care. She just wants 5. Because that's how the preferences were defined. Only the best roommate counts. So if you put 1 with 5 and 4, you can do this, but you won't be able to prove that this is Pareto optimal. Because you used 1 degree of freedom, which you did not need for the optimized notion. So 1 takes 5, and then 2 is the second dictator. What does 2 do?
Take 1.
Exactly. 2 takes 1, which means 2 joins this room, and poor 5 is put up with people who chose him. That's it. So number 3 is there and tries to take 2, who is already in a full room, 5, who is in a full room, and then goes for 4. So they open up a second room. What does 4 do?
Nothing. I mean,
Should stay with 3.
Exactly. 4 just says, yeah, fine for me. 4 does nothing. 4 says, 3 is already here, end of the day. Then a number 6. Number 6 will try 7, which she will succeed in. 7 will try 1 and then 2, and that doesn't work. So 7 will go for 9, and poor 8 will go to 3. Okay, so of course it's not a proof, but I hope you have a feeling why this is Pareto optimal. If you assume that there is some person who could be made better off, then you go to that iteration where this person got her roommate, and you can show that you can make this person better off potentially, but only at the cost of making somebody else worse off. And this is forbidden in Pareto optimality. This is how all Pareto optimal proofs are done, basically. Okay, so this was the easiest case, second problem. You still have strict and complete lists. And now the worst roommate counts. We stick to 3-person rooms. So what's the step of number 1 now? You want to have a worst roommate who is as good as possible.
So 5 and 4 now?
Exactly. Thanks, Andre. 5 and 4. Because, I mean, the second best roommate is the best worst roommate in a 3-person room. And then she already fixed the room. So number 2 tries to fix 1, impossible, 4, 5, also impossible. So after this, 9 and 8 are the available ones. She fixes that room with those 3 people, done, and then 3 takes the remaining 2. Simple one. Okay, now comes the tricky part in the third algorithm, and last algorithm to design. You have strict and complete lists. Again, the worst roommate count. But now you have varying room sizes. So not all rooms are of size 3, but you have small and big rooms. But still, everybody wants to be with the best worst person possible. What does number 1 do?
Picks 5 and go.
Exactly, picks 5, because if she picks a larger room, she will just get the worst roommate, right? So she will picks 5, and that's it. Room is closed. And then number 2 wants to join this room, which she could actually do, but by that you would make 1 worse off, which is against the principle of zero dictatorship. So number 2 will say, okay, then I will take the second smallest room and fix 4 and 9, the available agents upmost on my preference list, and 3 takes the remainder. 3 is not very happy with this, but yeah, life is like that sometimes. Okay, so these are the 3 algorithms. They are really not very sophisticated. They were easy to come up with, but the landscape, I think, is the main value in this paper. In general, they are cute algorithms. I like them. So this is the summary of the talk. So we studied Pareto optimal collisions of fixed size. We saw that verification is always hard. Existence is hard if lists are incomplete, and it's guaranteed if lists are complete. And finding the Pareto optimal assignment is easy in the 3 listed cases. You saw the algorithms, and it's hard in all the other cases. So open questions, which I promised. This is a really cute topic. It was really easy to start with. So Petra, the student on this, was a master's student, and she really enjoyed working on this. And Pareto optimality is, as I said, just one optimality criterion, not necessarily the best one. I would totally be into doing some similar work on envy freeness or group stability or popularity or whatever your optimality criterion is, which can be defined on preferences. You have to be careful though, because there's lots of literature on this. And before you start digging deep, you have to really read deep what's known and what's not known. And then player satisfaction is really a poor choice, I think. We chose this because this is very often in the literature, this best and worst choices, but it's really not the best utility function in reality. So you can pick your favorite utility function, the average of the quality of the roommates. Or you can put some cardinal preferences instead of ordinal, which don't have the simplest function, but some submodular function or something like this on it. Or you can put like some conflicts that if this roommate is in there, then that roommate shouldn't be in there or something like that for one person. So you just pick your favorite utility function, but it should be general enough to be interesting and not too general, because then it's not solvable. If you go up to high-order games, everything becomes hard. And Harris and Coates already realized that. Also, preference lists. So you don't have to stick to weakly or strictly ordered preferences. You can go for master list, which is basically that everybody derives the list from the same list. It's not always necessarily the same list for all players, but some fraction of the same list for all players, for example. You can also go more general. You can go for posets of sets of or sets of pairwise comparisons instead of a stricter weak order. And somehow I missed one point. So my fourth point was, which is not on this slide, I probably forgot to compile, is that in realistic scenarios, you have lots and lots of tasks when you actually search for coalitions. And you pick whatever scenario you're closest to, and then ask the real decision makers what the input properties and the output requirements are. An example, I play squash, and I'm sort of close to a training school where people are trained to become squash trainers, and they have a schedule on whom they play with, and they are to be grouped in constant groups. So it's an offline problem where they play on a regular basis with a person who is a bit weaker than they are and the person who is a bit stronger than they are. This is how you improve. And there are some preferences, like one man, one woman partner is always healthy for everyone, and so on. So you have these sort of preferences, and based on this, you can judge the quality of a coalition. Whatever real application you have, let it be squash or chess or whatever you like most, go for it, and then try to make a coalition formation problem out of it. It's nice. It's really nice to play with, I think. So thank you very much.
Okay, thanks a lot for a very nice talk.
Okay, let me ask the question more specifically. So I guess the answer is anyway that hopefully nobody studied this, but I was just wondering, like, the condition that you have to judge everyone who will end up in your room seems unrealistic to me. I mean, I have one application in my mind, which is I just put my oldest son into the basic school, and there you got a form, and if your child is accepted to the school, there will be 3 classrooms in the school. And they ask, is there someone who you would like your child to specifically be with? And then there is a question like, is there someone who your child you don't want to specifically be with? Yeah. And it's just like, there are like few people that you want to be with. Then there is a huge number of people that you don't care. Mm-hmm. And then there are few people that you don't want to be with. Yep. But you will end up with most people that you didn't judge at all. Yeah. But what you care is like the worst and the best anyway.
Yeah, I think this application wonderfully merges my point 2 and 4, which is not on the side but is supposed to be there. 4 is that a real application where you form coalitions, and 2 is that this satisfaction function is really just for the theoretical purpose. Your satisfaction function is basically you have some people on whom you have satisfaction 1. These are the people you want your kid to be with. A bunch of kids with whom you have satisfaction 0. These are the people who you don't know. And a couple of the kids who used to bully your kid in kindergarten, and they have satisfaction -infinity.
Yes.
And then you do a cardinal version instead of an ordinal version. And this makes a lot of sense. And they are trichotomous preferences, which is also very common in matchings or correlations on their preference literature. So you only have 3 sets, trichotomous sets. So I don't know if this has been studied, but it definitely makes a lot of sense to study from this perspective, for example, a similar problem.
Okay.
Yeah, I think that there was something like this in hedonic games. Is studied like this friends model and the enemy model.
Mm-hmm.
Yeah, so, but there you always have like one or the other.
Mm-hmm.
And yeah, well, let me be also curious. This like this thing with measuring the worst is like a Chamberlain Quran in rule in committee elections.
Mm-hmm.
Do you think does it make sense to really like introduce other notions from committee elections into your problem to like specifically say like keyboard or something like that?
Possibly. I'm in the stage of learning about elections and voting, an early stage of this. So definitely, if there is interest in that, I would be totally into like looking into any other rule being translatable to a coalition setting in this sense. I know that there are rules like that there are voting rules which translate readily to matchings very nicely.
Mm-hmm.
So there might be, and those are quite nice papers which show these connections. So if there's any connection that we could discover there, that would be really nice, I think.
Yeah, that would be great. And
maybe on this transition from matchings to the rooms of size 3, I was wondering, like, I guess the answer is nobody studied that, but hopefully. But I was just wondering, like, if you have very few rooms of capacity 3, and all the other rooms have capacity 2, whether somebody studied like this.
I think you probably can parameterize basically by number of 3-person rooms. Probably the old approach of you just fill up the 3 rooms like in constant many steps, basically, and then do the matching problem for the remainder, and then compare the outcomes. So the matching problem you can solve to optimality for the remainder.
Mm-hmm.
So it should be doable. I don't know whether there is anything written down or any most efficient algorithm for this.
Yeah, because like the naive approach would lead to an XP algorithm with this parameter. Yeah. But Andrea would definitely love to have an FPT algorithm. For
Exactly. So
or kernelization, I mean.
Even.
Yeah.
So there is a recent, I'm into popular matchings, which some of you might know. That's a notion which came basically from voting, got translated into matching and got very successful. And there is a very recent paper on popular matchings with room size 2 or 3. But that's a different notion. So.
Yeah, for roughly like for rooms of size 3, we've done some work last and this year with Klaus, which will be published in Wine.
Yeah, which got the best paper award, wasn't it?
It got. I'm not
no, that was not a paper of Klaus, which got published in Wine. Sorry, Klaus writes too many papers.
Yeah, he's kind of great.
Yeah.
I don't know whether this one. No, I'm not aware of getting.
No, that was Klaus and Niklas, I think, together.
Yeah, Klaus and Niklas. Yeah, that one. Yeah. Mm-hmm, yeah. So this one is without Niklas, but so that's Robert. Yeah, so yeah, there we actually used like yeah, we were working on three-dimensional matching, but then to get at least something we derived from master lists. So yeah, that could actually lead to something interesting.
Yeah, master lists are cool. They make problems easier.
Yeah. Like maybe for this application of Ondra, we can probably use like how was it something like graph envy-freeness that Robert Brederick at some point introduced. So like you only think about your neighborhood and then maybe measure on that some it's not really like the acceptability graph, but it's a different graph in which you actually measure things.
So you can only be envious of people whom you know.
Whom you know, yeah, and the others.
I think it was Kotka and Edith, right? I think. And anyways, yeah, I know the setting.
Yeah.
But,
yeah, that might be interesting as well.
Okay, then maybe one more question, like, what is it that the dictatorship for the best person in the room only works for fixed size rooms?
That's a good question. Go back to the summary slide. So here, this one. Right, so your question is this part, right? The upper right corner.
Yes.
Let me try to remember. Yes, I remember. So you have strict and complete lists. Only the best person counts. And if you try to do the dictatorship, you will realize where the hardness sneaks in. So for number one, what matters is only the best neighbor. Yes. So she ties herself together with her best choice, and they are not to be separated later. And then number two ties herself together with her favorite person. And the number three possibly ties herself together with the first room. So you have unbreakable coalitions of differing size, because you never fix the room size when you tie the people together. And after a while, your question will be whether coalitions of a given size could be still packed together in coalitions which have this array that you are pre-given. And this is a partition problem, or a sum problem, basically a subset sum problem. So from subset sum, you can construct such preference lists that at the end go out to this question.
Mm-hmm. But it's not clear that already if you have room size 4, then everything breaks down.
No. You have to check the subset sum problem basically when it is hard.
Okay.
Mm-hmm. But you have an array of numbers, and you wanna like sum subsets of them up so that each subset has a sum which is in a pre-given other array. And I don't know what objective array this ends up being NP-complete to.
Yeah. Mm-hmm.
Cool. So are there any other questions or suggestions or whatnot? Doesn't seem to be the case, so we can probably thank the speaker yet again.
Thanks for the attention and for answering my questions.
Thank you very much.
Thanks a lot.